So we are on to 1.3a, properties of functions, odd and even functions, okay? So our first objective that we are hitting is determine if a function is an even or odd based on the graph. So following along in your first blank, it says a function f is even if for every number in x, it is in the domain, x is in its domain, the number negative x is also in the domain, okay? And this is the rule that we follow. F of negative x has to equal x. So then these two things have to be the same, which just basically means that if -1 is 4, then +1 has to also be 4. Okay, those have to be equal values. Okay, so for an even function, for every point xy on the graph, the point -xy is also on the graph. So a very basic example would be if I have -x here, +x here, y here, the graph is going to cross both of them at that same point. Pretend that was better, but so we're going to pretend that was perfectly drawn. Okay. So that's what you're looking at on the graph. Are the points matching up? All right. Next, a function f is odd if for every domain x in its domain, the domain -x is also. However, it's different. So f of -x has to equal -f of x. So the y is negative. The y's are opposite. So for an odd function, for every point x, y on the graph, the point -x, -y is also on the graph. Your x's and your y's are opposites. Okay, so an example of how that could look is, again, pretend that Miss Jones is the best artist you've ever seen. So if I have -x, -y, I also have to have and again, these are all perfect curves and they're equal. It's equal, it's perfect, it's beautiful. We'll get it more graphically better here a little bit. Don't judge me. Okay. So that's what that looks like. Now, theorem 1, it says a function is even if and only if its graph is symmetric with respect to the y-axis. Okay, even. So if you think about even, think about evenly split. Does the y-axis evenly split it? Then we have a function is odd if and only if its graph is symmetric with respect to the origin. And we talked about symmetry yesterday. Origin symmetry means that it has rotational symmetry. Okay, please make sure you're paying attention to this, because if you ask me for help and you're not taking notes nor paying attention while I'm teaching, I'm going to give you that same energy. And yes, that's recorded. So be mindful of that. I may play a game and listen to music and text somebody. See how you feel when you're trying to get help. Okay. Questions, comments, concerns so far? All right, so let's put these words into action, because it kind of can be like, what the heck is happening? All right, so here we have a function on a graph. I know it's a function because it passes the vertical line test, so I can call it a function. And I want to determine if it's even, odd, or neither. So when I look here, the number one sign for recognizing whether it's even, odd, or neither is if your y-axis evenly divides it, then it's even. Does my y-axis evenly divide this? Yes. So this makes it a even function, okay? Because it has that symmetry with the y-axis. Make sense? Okay, let's try another one. This one. Well, we're in check for even. Does my y-axis evenly divide it? No. Does it have origin symmetry, meaning that if I was to rotate this, would it be the exact same graph? No. Those two things are your quick check on whether it can even be even or odd, okay? And because it does not pass either test, then it is neither even nor odd. There's no y-axis symmetry and there's no origin symmetry. Nate, is function C even or odd? And why? Close the game. Isaac, even or odd? And why? And why? Thank you, Isaac. It has origin symmetry. Okay, so therefore it is an odd function. It goes through the origin, and if I was to rotate this 180 degrees, guess what? It would be the same function. All right, questions about identifying graphically whether it's even or odd. Do you feel like this is something you could do? Yeah, doable? Okay. All right, now we're going to talk about it from a different perspective. Identifying even and odd functions from the equation. So we did it from the graph. Now we're going to identify it from the equation. Okay. So example 2a, identifying even and odd functions algebraically. When you're identifying them algebraically, you are testing the rule that you set in place. So you set that f of x, for it to be even, f of x has to equal, let me write even, f of negative x. That means when I substitute in negative x, my equation is unchanged. Okay, for odd, we got that. What was the rule for odd? We wrote f of negative x equals negative f of x. Okay, now a quick identifying factor for this: if something's even, then its highest power has to be even. If something's odd, then its highest power has to be odd. So that's the first thing you want to check. Is the power, the highest power of the equation, even or odd? Okay, so we look here. What is our highest power? 3, and what is that? Odd. So we're going to test for whether it's odd or not. Okay, so for the odd test, you're going to find f of negative x, and you're going to find negative f of x. Do you see how this is tying into stuff that we've already done? I hope so. Operations on functions taking place here. So I'm going to substitute in a negative x into this. So this gives me negative x to the third plus 5 times negative x. I don't know why I put an extra parenthesis there. This gives me a negative times a negative times a negative is still a negative. And 5 times negative x is negative 5x. So that's what I got on this side. So f of negative x equals negative x cubed minus 5x. Now on the other side, I'm going to test to see if I get the same thing. When there's a negative on the outside of a function, what is that doing to all of the terms? It changes their signs. So negative f of x equals negative x cubed minus 5x. Are these both the same? Yes. So guess what that means? Yes, it's even odd. And that's how you algebraically show that two functions are odd. Okay, so we found f of negative x, we found negative f of x, and they were the same. And since they were the same, guess what? It's an odd function. Got it? All right. Questions about verifying whether it's even or odd so far? Okay, let's do another one. Here we have 2x squared minus 3. Okay, again, we're going to start off with what is the highest power? What is our highest power? 2. So which test am I going to run? Even, because my highest power is 2. I'm checking that the original equals f of negative x. So because you're doing even, you only have to verify one thing. You already have the original. You're only having to find f of negative x. In this case, it is g of negative x. Because what is the name of our function? G. So we have 2 times negative x squared minus 3. What's a negative times a negative? A positive. So we get 2x squared minus 3. Is this unchanged? Yes. So guess what this means? Yes, it is even. Because it's unchanged. They have to be equal to each other. No, you're only testing for even because your highest power is 2. If it had been different, then it wouldn't have been odd. I can go back. Because the rule that we wrote to test, we wrote the rule for the definition. And the definition says that if something is odd, you're going to test to see if f of negative x equals negative f of x. If it's even, you're going to test to see if negative x equals f of x. So this is what we're testing. And because it's even, we already have f of x. So we're just verifying that negative x is still going to be unchanged. Got it? Good question.
So the even is always f of negative?
Even is always f of x equals negative f of x. And odd is going to always be f of negative x equals negative f of x. Odd has a little more to do, but all right. I would like for you guys to do example 2C. So you guys are going to do 2C and then verify with your peers. Let's check you. All right, so when we look at the power, we see that it's a what? What test are we gonna run? We run the odd test, right? Why are we running the odd test? Because our highest power is 3. So that means we have to check for f of negative x, and we have to check, not f, what are we at? We're in h. We're h. This function is called h. So we have h of negative x, and we're going to do negative h of x. Okay, so that gives us negative 4 times negative x to the third plus 1. And that gives us a negative times a negative is going to make a positive.
Oh my God.
So that's that side. Then we're going to do negative h of x. When the negative's outside of the function, what does that mean you're doing? Switching the signs of every term, right? So we're changing the sign. So instead of a negative 4x cubed, it becomes a positive 4x cubed. Before size a positive 1, it becomes a negative 1. Are these exactly the same? No. So it's a no. So therefore it's neither. It is not odd nor even.
Yeah, let's go.
Okay, how do we do?
Ah.
Yeah? All right, so the remainder of the period you're going to be using to work on your assignments.
Yeah.